So let's continue with lecture 45, where we're gonna solve this example, example 8.10. Parallel reactions in a plug flow reactor with heat effects. The following gas phase reactions occur in a plug flow reactor. Reaction 1, A is converted to B, and in a parallel reaction, you have 2A, 2 molecules of A converts to C, and both the rate laws are given. You can see minus R1A and minus R2A. Pure A is fed at a rate of 100 mole per second, a temperature of 150 degrees C, and a concentration of 0.1 mole per liter. Determine the temperature and flow rate profiles down the reactor. Let's see what informations are given. So delta H reactions are given. You can see that delta H reaction 1 means for reaction 1 A, that means based on 1 mole of A, that is minus 20,000 joule per mole of A reacted in reaction 1. Then we have delta H reaction 2A. You can see that there is 2A here, see? So, which means it's for reaction 2 based on 1 mole of A reacted. So let's read the value and the units. Minus 60,000 joule per mole of A reacted in reaction 2. The CPs are given, CPA, CPB, and CPC. So you can, the moment you see the CPs, you should go ahead and calculate the delta CP so that you can understand, or you can know if the reaction of the delta H reaction are a function of temperature or not. طيب, what else is given? K1A is given. Tamam, K1A is given. Of course 1A because the reaction is based on 1A. And then you have E1 over R is given. Then you have here KE2 and it's K2A half 1, and here you have 2A as well. Tamam. Okay, see, you have 2A here, then you have 2A here. You have 1A here, so that means you should have 1A as a subscript for the K as well. Tamam. So we are fine. And E2 is also given, E2 as divided by R. Okay, so let's reflect on these values. So what do you see? Well, obviously E2 is greater than E1, right? E2 is greater than E1. What does that mean? That means reaction 2, the rate of reaction 2 is more sensitive to temperature compared to the rate of reaction 1. Tamam? So we all know that if we increase the temperature, both K's will increase. K1A and K2A will increase. However, K2A will increase more than what K1A will increase. Okay? For instance, if we increase the temperature to a given value, K2A will increase, for example, 3 times, but K1A will increase only maybe 1 time. Something like this as an example. Okay, but which one is more? Well, that's a different story. Which one is more depends on the Arrhenius constant, the E, okay, and the temperature. Okay. Let's look at the coolant. We have coolant as well. So the coolant is given here. Temperature of the coolant, TA, and UA is given as well. You can see that it is U times A small, which is the surface area per volume, because you can see that the unit here is per volume, not per area, تمام, or it's per something. Okay, طيب. Well, apparently this reaction, both reactions are exothermic. تمام, both reactions are exothermic, so I do need cooling, correct? I do need cooling, so I'm providing coolant, and the coolant, there is no information about the mole flow rate or the mass flow rate of the coolant, so that means the coolant is going to stay at, will be at constant temperature. It's going to be at constant temperature. Okay, probably I'm generating steam, so you know, water boils at 100 degrees C, so I'm providing the coolant as a saturated water, saturated liquid water, and as it absorbs heat from the reaction mixture, it keeps evaporating. And this is how you remove heat. This is how water is removing heat from the reactor without its temperature being increased. طيب, enough reflection. Let's go to the solution. Okay, let's go to the solution. طيب, of course, we want to run the profile, right? We want to run the profile and see how the molar flow rate profiles look like. Okay, that's good. So that means we need to go through the algorithm, the design algorithm. Well, the design algorithm consists of 5 steps. You know where it starts from. However, okay, it starts from the design equation, from the mole balance. However, by now we know that for non-isothermal reactor design, temperature is variable and we need energy balance. So we can start with step 0. Step 0. What's the step 0? Step 0 is where you write the energy balance. طيب, so let's start with energy balance. Okay, so here we have, this is the general energy balance. Can we write it specifically for this reaction? Yes, we can. Okay, so let's write it together. Okay, dt by dv equals summation of, so you have the product minus r multiplied by minus delta H, right? We are summing this. How many terms do we have? Well, we have 2 terms because we have 2 reactions. Okay, we have 2 terms because we have 2 reactions. Okay, let's write these terms. Start with reaction 1. So that would be minus R1 blindly. And then I open my eyes, look for the reactants in reaction 1. The only reactant we have is A. So it will be A minus R1A multiply by, I close my eyes again, minus delta H reaction, and obviously I will write 1A as well. Tamam? Okay, then I open my eyes. Well, you don't have to, not yet. Okay, we write minus R2 because that's for reaction 2, and open my eyes, look at the reactants of reaction 2. The only reactant we have is A, so that would be 2A. I close my eyes and write minus delta H reaction, tamam, also 2A, so that's for reaction 2 based on mole of A. Okay, and then you have here minus U times A times T minus TA. Okay, so U times A times T minus TA, and then divided by summation of Fi Cpi. Now the summation is over all the species. Summation is over M, where M is number of species. How many species do we have? We have 3, so we have 3 terms. So that's Fa times Cp A plus FB times CPB plus FC times CPC. 3 terms. Okay, what can we call these terms? Easy. So these, let's look at minus R1A. It's always positive, right? And minus delta attraction 1A is always positive as well. Okay, so this is positive, and its friend minus R2A is positive as well. So this whole, these two terms, we'll call it what? The localized heat. The localized heat generated, right? The localized heat generated by the reaction. What do we call this guy? What do we call this guy? Okay, let's first look at UA is positive. T is greater than TA. Because T naught is 150, and then the temperature might increase. Okay, and T is only 100 and stays 100, so that's positive as well. So this is the localized heat removed, right? The localized heat removed. The localized heat removed. Okay, what is this? This is the heat capacity of the reaction mixture. Okay, heat capacity of the reaction mixture. طيب. I have a question now for you. The question is, how can you calculate the standard delta H reaction at TR and the delta H reaction at T for reaction 2? Okay, so how can we do this? Well, let's see how we can do this. As you can see, Shabab, in the energy balance equation, we needed what? We needed minus delta, well, let's see, it was minus R2A, صح? Multiply by minus delta H reaction at T for pair. This is minus delta H reaction 2A as well. Okay, tamam. So here you have 2A, tamam, and here you have 2A as well. So what is the unit of minus R2A? Well, it is mole air reacting per, for example, second, per liter. Tamam. And let's see what minus delta H reaction 2A is. It's joule, صح? Joule energy released. tamam. So delta H reaction, the unit is joule. Usually it's kilojoule, but you have to convert it to joule, so it will be consistent with the CPs as well. Per mole of A reacted. Adil? That's how you cancel out here mole of A with mole of A. Okay, so now the question is, how can we calculate this term, the minus delta H reaction 2A? Okay, well, we know how to do this. Adil, we know how to do this. So let's go ahead and write this equation. So delta H reaction for reaction 2 based on A at any temperature equals standard delta H reaction for reaction 2 based on reactant A at T reference plus delta CP for which reaction? Yeah, for reaction 2 based on which species? Based on species A. So you have here 2A, we have here 2A, and here we have 2A, and here we have 2A. They're all for reaction 2 based on reactant A. Tamam. Okay, multiply by T minus TR. Okay, good. So that's why we have a question here, that how do we calculate this guy? How we calculate this guy? Well, you know that delta H reactions are calculated from delta H formation. Delta H formation. So again, this is for for 2A. Delta H reaction 2A. That means it's for reaction 2 based on 1 mole of A reacting. 1 mole of A reacting. Which means you need to rewrite this equation, because this equation now is written per 1 mole of C produced, but here we need delta H reaction per 1 mole of A reacted, because it's based on A. It's based on A. Tamam? Based on A. Based on A. See, even the rate is based on A. Okay? Tamam? So that means we will rewrite this as A gives you half C. Okay? Tamam? Now, let's do the calculations. Okay. طيب, let's look at delta H reaction, standard delta reaction at TR. We find it from the delta H formation. صح? So we have half times delta H standard delta H formation for C. Okay, tamam, at TR minus yep, standard delta H formation for A also at TR. So now you can see the units here should be joule per mole of A. صح? If I use this reaction the way written here, it will not be per mole of A, it will be per 2 moles of A. And that's something I don't want. I want per mole of A. Okay, let's look at the delta Cp. The delta Cp, which is also for 2A. Remember, this guy was also for 2A. Tamam? Equals. Now, where do you take it from? Do you take it from this? No, we don't. Okay, the whole calculation is per mole of A, so we take it from here. Okay, so that is half CpC minus CpA. Tamam? And of course, in this case, we know that the Cp here, the half 180, I believe it was 180, and this guy was 90, something like that. Okay, so it will go to 0. Tamam? The same thing with delta Cp for reaction 1. Delta Cp for reaction 1 based on A, it is Cpb minus Cpa, and they are both equal, so it will be 0. So that means both delta H reactions are not function of temperature. Okay, so again, if you want to put a unit here, if you want to put unit for this guy, it will be joule, صح? Joule per mole of A per Kelvin. If we extract it from this stoichiometry, will be per 2 mole of A. Then this is something we don't want. This is something we don't want. So let's see now. This term is per mole of A. This term is per mole of A. Therefore, this term will be per mole of A as well. That will be correct. So please pay attention to these things, these details. Right, so let's go to the algorithm. Let's go to the algorithm. Step 0, energy balance. We wrote the energy balance, and after writing the energy balance, of course, you need to frame it, and then you will provide the initial condition at V equals to 0, T equals to T naught, obviously, which was 150 degrees C or 423 Kelvin. Tamam. Okay, then we ask ourselves, did we really produce any or introduce any variable? We'll check, is U a variable? La. Is T a variable? No. Tamam. Is delta H reaction 1A is variable? Well, we just calculated it previously in the previous slide, and we saw that the delta Cp for reaction 1 based on A is 0, so that means delta H reaction is not variable, it's constant, it's not function of temperature. The same thing was for delta H reaction 2A. Tamam. Okay, good. Is the CP's variable? No, they are constant. Okay, minus R1A and minus R2A, are they variable? Yes, they are, and we're going to take care of it in the step number 2, which is writing the rate law. طيب. Okay, so we're done with the energy balance. Let's go to the design equations. So let's go to the design equation. Okay, so here, Shabab, are you going to use design equation written in terms of X or written in terms of molar flow rate? Well, we have multiple reactions, right? So we're not going to use X. X is not my preferred variable. It's useless. Okay, so, well, not that much useless, but it's not as useful as the molar flow rate. So we write a design equation in terms of molar flow rate. So we have dFA by dV equal RA, dFB by dV equal RB, and dFC by dV equals RC, and we need to provide the initial condition. At V equals to 0 if A equals 100 mole per second, if B equals to 0, if C equals to 0, and you need to frame the initial conditions and all the equations as well. Okay, let's go to the rate law. We have two rate laws. So we have two rate laws. Okay, here we go. Tamam. Okay, very good, very good. Okay, what else? Well, let's look at the rate constants. We know that the rate constants are not constants, right? They are a function of temperature, and we know that the temperature is changing. So these guys are variable. Since they are variable, I need to provide an equation for. Okay, so here we go. These are my equations for K1A and K2A. Any other thing which are variable in the rate laws? Yes, the concentration. We go and provide this in the stoichiometry step. Hello, Shabab? Okay, so let's move forward. Stoichiometry. So we have a gas phase reaction and run-in plug flow reactor. So delta P could be assumed to be 0. Okay, where do we start with the stoichiometry? Any guess? Yes, you guessed it right. We have here RB and we have RC, but we only provided equations which are suitable for RA, correct? So the first thing we need to write, okay, is RA net, because all the equations, all the rate laws are actually for the individual reactions, 1A and 2A. I did not even provide an equation for RA. So that means I'll need to write the net rates. Okay, I'll need to write the net rates. I need to write RA net, RB net, and RC net. Okay, let's do that. So RA equals R1A plus R2A, correct? Blindly, right? Because I know A is involved in both reactions. What about RB? Well, RB is involved only in the first reaction. So B is involved only in the first reaction. Tamam. So here RB equals R1B. What about RC? Well, RC, C is involved only in the second reaction, so it's RC equals R2C. Okay, now we're good. Now we are good with all the RBs. Tamam, and now we need to relate the R here. Relate the R1s and R2s to the equations we have. Let's see. R1A. Yeah, R1A. We have it here. Okay. Tamam. Let's see R2A. Oops, we have it. Mumtaz. Tamam. What about R1B? Well, we don't have R1B. Right? Do you see it there? No, we don't see it. Okay, so let's get R1B. Tamam. And the same thing, let's get R2C. How do you find it? Well, we see it from the relationship. We know that R1A divided by minus 1 equals R1B divided by plus 1. صح? And we know that R or reaction 2 based on A divided by minus 2 equals R2C divided by plus 1. And from here we get the relationship. Tamam? So from here we know that R1B simply equals minus R1A. And we know that R2C equals minus half R2A. Okay, so that's the second step in the stoichiometry. Okay, good. Then we go to the concentration. So where do you start? Well, you know where you start, right? You start with Ca equals Fa over epsilon, right? And Fa remains Fa. I want molar flow rate. Epsilon equals epsilon naught times Ft divided by Ft naught multiply by T divided by T naught multiply by T naught over P. Can we simplify? Yes. This one equals to 1. Why? Negligible pressure drop. What about T over T naught? Can we take it to 1? No, because the operation is non-isothermal. Okay, temperature will vary, it could vary. What about if T over if T naught? Does it go to 1? Well, let's look at the stoichiometry. If we had only reaction 1, then yeah, if T will equal if T naught. However, we have, look at reaction 2. You have 2 moles of A reacts to form only 1 mole of C. So that means as the reaction progresses, the total number of mole decreases. So Ft over Ft naught is not 1. Okay, we need to leave it there. Okay, so what shall I do? Continue. Well, you have here Ft naught divided by epsilon naught, and then you have here Fa divided by Ft, and then we have here T naught divided by T. Okay, divided by T. Okay, so what about this guy? This guy becomes Ct naught. Tamam. So now we have an equation for Ca. Ca equals Ct naught times Fa over Ft times T naught over T. Well, good. Thank you very much for this nice equation. Okay, we can write also Cb and Cc, but in fact they are not necessary, because if you go upward and look at all the framed equations, you do not see except Ca. You don't see Cc and Cb. Okay, so we don't need to write it there. Type. So we said we have an equation for Ca. Ca equals Ct naught Fa over Ft times T naught over T. Okay, what comes next? Well, you always check, did we introduce any variable? Tamam, and then from there you can answer. CT naught is not variable, FA is variable, but we have an equation for FA. T naught not variable, T is variable, but we have an equation for T. And FT is variable, therefore I write an equation for FT. So FT equals FA plus FB plus. Okay, tamam. So let's look at the solution. So one would say here, oh, but V is not given. So what? Don't freak out. Don't panic. That's fine. Put any V and you check. For example, if you choose V equals to 100, you will soon realize that you do not need to plot till 100. You'll need maybe to plot maximum till 1 liter. Okay? Tamam. So let's look at the profile. So what's happening to FA? Well, FA is decreasing. So FA is decreasing. What's happening to FC? Well, FC is increasing. Tamam. FC is increasing. What's happening to FB? It's increasing as well. Tamam. Until you reach around half a liter, 0.5 liter. So that means we don't even need to plot up to 1 liter. Maybe plotting up to half a liter would be enough. But that's fine. Let's plot it so that we can see what's happening to the temperature profile. Okay, the first, let's see why we have more FB than FC. Why is that? Well, the reason could be two. First, we know that every mole of A reacting will produce for you half mole of C, while every mole of A reacting produce for you 1 mole of B. But also, the reason could be that the rate of the first reaction is much faster. Okay, the rate of the first reaction is much faster. We'll come to this in the next slide. Okay, tamam. So we answered this question. Is it necessary to use a 1 liter reactor? No, we can use smaller. Tamam. Why does T go through a maximum value? Well, that's good. Let's look at T. Actually, T has different behaviors. Initially, it increases at a small pace. Okay, then it increases dramatically. Then it reaches a maximum value. Then it decreases. So what's happening? Well, of course, we'll need to plot the localized heat transferred and the localized heat generated. Tamam? I'll leave this to you to do at home. But obviously, throughout the reaction, from 0 liter to 0.5 liter, where the reaction stops. Okay, so here the reaction stops. Throughout the reaction, the rate at which heat is generated from both reactions is more than the rate at which we are removing heat. So obviously what will happen? The temperature will increase because energy stays inside. When it stays inside, it heats up the reaction mixture. Tamam? Yes, I'm removing part of it. So this heat which is released from both reactions, I'm removing part of it, but the other part staying inside. What will it do? It will increase the temperature of the reaction mixture. Tamam? But then what's happening? Why suddenly it increased? Well, remember which rate constant is more sensitive to the increase in temperature? You know that reaction 2 is more sensitive to the increase in temperature, right? Because its E is more. So as you see, temperature is increasing, both rates are increasing, but you'll see that the second rate was increasing, the second rate constant is increasing more. Okay, that means the rate of reaction 2 will increase a lot, and since the amount of energy it releases is 3 times more than the energy released from the first reaction. Now you can see a shoot in temperature. Okay, you can see a shoot in temperature. Okay, what else? Well, if we have a shoot in temperature, so temperature is very high. Now the delta T between T and TA now becomes very large. Now the localized heat transfer becomes very large, tamam, and it becomes larger than the localized heat generated because the rate of reaction starts to slow down because the concentration of air dropped dramatically, and that's why the temperature starts to decrease, tamam, and it will continue decreasing because now after 0.5 liter we don't have any reaction. All what we have is heat removed from the reactor, tamam, and apparently the value of U, the overall heat transfer coefficient, is not that big. That's why the temperature is not dropping fast. Okay, so we said what other variables could be useful to plot. We said localized heat generated, localized heat transferred, the rates is useful to plot. Tamam. You can also plot the localized heat generated from each reaction and so on. So please look here. We plotted T and we also plotted rate 1, which is in green, tamam, and rate 2, which is in blue. Okay, so as I said, we can plot many other things. We can plot the localized heat generated, localized heat removed, the localized heat generated from reaction 1, the localized heat generated from reaction 2. Okay, all of these we can plot, and please plot them at home so you know exactly what's going on in the reaction and the reactor. Okay, so let's look. Remember, Shabab, I told you the reason behind why we have more B compared to C is not only the stoichiometry but also related to the rate of reaction. See here, the rate of the first reaction is more than the rate of the second reaction. The rate of the first reaction is more, although the, well, not although, I mean the rate of the first reaction is fast because the Arrhenius constant is large, because the activation energy is low. Tamam. Okay. طيب. So what's happening? We said the localized heat generated is more than the localized heat transfer, so the temperature continues increasing. The temperature continues increasing. Tamam. Okay, and therefore, see Shabab, rate 1 is increasing, rate 2 is increasing as well. However, when we have now this increase continuing, tamam, and the rates, we said, you can see Shabab here, you can see it clearly here. Tamam, you can see it clearly here. The rate at which, the pace at which rate 2 is increasing is more than the pace at which rate 1 is increasing due to the increase in temperature. Tamam, due to the increase in temperature. So you can see Shabab now, the rate of the second reaction is increasing faster. Tamam, it's increasing faster. Both are increasing, but the rate of the second reaction is increasing faster because it's more sensitive to the increase in temperature. So you can see now the rate of reaction 2 here is more than the rate, tamam, of reaction 1. And you know that the delta H reaction 2 is much more. So that's why you see that sudden jump here in the temperature. Okay, and we explained the rest. So please go ahead and plot all the other variables that we talked about and analyze the system more. Analyze the system more, and this is how you learn more concepts. So that if we ask you multiple choice questions regarding concepts, you would be answering them correctly. Tamam. So with this, we finish this example and this segment of lecture 4.8. Actually, we finished lecture 45, sorry, and we'll see you soon in lecture 46. Good luck.